So here is one of the deep sky objects this year is Sirius B. This is a Chandra image of Sirius B and A. It's a binary system. Sirius, you know, is Alpha Canis Majoris, the dog star that follows Orion around in the sky. Well, it actually has a white dwarf companion, Sirius B. This is a Chandra image. This is an optical image from McDonald Observatory, and ignore the diffraction patterns here. That's an artifact of the instrumentation. But what's important here is, and here again I can fool you if you're not paying attention to multi-wavelength astronomy. This is the Chandra image. Now, white dwarfs are very, very hot. But on their place at the lower left-hand section of the HR diagram, they're very, very dim because they're very, very compact and small. So you can't see them very well. So you can see them in X-ray really, really well. So this very bright source is the white dwarf. That is the companion with the Sirius A, which is what you see when you look up in the night sky. But of course, they're too close together and too far away for you to actually differentiate these two objects. So this is from the McDonald Observatory, and on this one, the bright one is the primary star, and the little faint one is the white dwarf, because that's optical, and you can't see white dwarfs in optical. So that's why you need to look at different wavelengths of things, okay? So let's look at Mira again. We already said it was a variable star, a Mira variable star, pulsating on its way up to the red giant branch and then sitting there while it finishes fusing all of its nuclei. But right here we have this white dwarf. Now, the white dwarf, and this is an early Hubble image with this odd little bump on it, which now has been more highly resolved into actually a white dwarf companion. So this is a contact binary. Now, if you have two objects and they are close enough together that the Roche limit touches of those two objects, then at that point where the two Roche limits, and that's the limit within which a star can hold itself together under gravity, right at that point where they touch, you can have a transfer of matter. Now we have a white dwarf which has a very, very strong gravitational field, right? It's sitting down in a nice deep well in space-time because you have the mass of the sun and something about the size of the Earth. So here we have Mira, which is a red giant. So the outer envelope of red giants, like Mira, has extended quite a ways from the central core of the star, and therefore it's very loosely held. So if this outer envelope touches the Roche limit point, mass transfer can take place. And the transfer all that material will end up in an accretion disk around the white dwarf, which sets up a situation where a lot of interesting and exciting things can happen. Not for the poor little white dwarf sometimes. Because ordinarily a white dwarf could last forever. Okay, anything that's a very low mass star, less massive than the sun, every single thing that's formed since the beginning of the universe is still a red dwarf. Anything that's become a white dwarf is still a white dwarf, because it takes about 1 trillion years for those to finish radiating away all the energy they have and turning into a black dwarf. And the universe is only 14.3 billion years old, I think, at last count. So, we have a scenario here set up for destruction. This is a white dwarf. CH Sig is a red giant. It has a white dwarf companion. And this is sort of a symbiotic affair. Actually, this is a very, very dynamic system. There is a huge jet of material coming away from the white dwarf. Now, normally you don't see huge jets from white dwarfs, but there is a situation here where, just like bees and flowers, where bees use the pollen to produce their food and the flowers use the bees to reproduce by spreading that pollen, this white dwarf and this red giant depend upon each other. They're having an effect upon each other. And anything that happens to one is going to have an adverse effect, most probably, on the other one. The jets from the white dwarf and the stellar wind from the red giant are working together. Now this is a pretty, it wouldn't take too much to disrupt this particular system if something takes place. So this is a very likely scenario to lead to a type 1a supernova event. Euscorpii is another one. Euscorpii is a primary white dwarf, and it has a very low mass main sequence star. And it is thought that Euscorpii, this particular white dwarf, is massive as a white dwarf can be, which we'll get into in a moment, and exist. So it has an even stronger gravitational field, and this is a very low mass star, so it's not holding any of its material very tightly to the core of the star compared to the strong gravitational field of the white dwarf. So this is a very rare variable star called a recurrent white dwarf, novae, actually. You can have every now and then in any one of these systems, you have any star in a binary system with a white dwarf, and trust me, there are billions of these systems out there. You can have a little bit of that material from the accretion disk drop onto the surface of the white dwarf, and you have a nova. That's called a nova. This system is a recurrent nova. There's only about 10 of those known or so. They actually go nova about this one every 10 plus or minus 2 years. And so this one is so dynamic that this is a great scenario for a possible type 1a supernova event. It's very likely that this white dwarf will be destroyed because it is accumulating material from its companion star so rapidly.